Okay, we're still talking about mixtures of gases here, although we can be looking at one gas at a time. We want to talk about something called Graham's law. To kind of set this up, think of something you know. If you have a bottle of perfume and you spray the perfume or even break the bottle in a room, eventually everyone in the room, especially if you sprayed a lot or spilled a lot, everyone in the room can smell the perfume. When you smell the perfume, they've got this nice fuzzy cloud they've drawn here for you, but when you smell it, you're not smelling the liquid perfume, you're smelling gas particles that have traveled to your nose. There's your nose. And so those gas particles essentially are diffusing to your nose. This is called the process of diffusion. It is a common process. We're talking about it in terms of gases diffusing. You also can talk about liquids diffusing. This is something that's often used in biology. It might make sense, it probably makes sense, that gases do not all diffuse at the same speed. In fact, temperature has something to do with it. If the temperature is higher, at a higher temperature, gases will diffuse faster than if it's colder. At colder temperatures, gases diffuse slower, and at higher temperatures, gases diffuse faster. And this is because of something we talked about in the kinetic molecular theory. The kinetic energy of the gas is proportional to the temperature in Kelvin. So a higher temperature means there's a higher kinetic energy, and of course kinetic energy is the energy of motion. Now, we can relate not only at different temperatures, but if we're at the same temperature, different gases will diffuse at different rates. So if I have a sample of oxygen gas, it would diffuse at a different rate than a sample of hydrogen gas, even if they're both at the same temperature, which means they both have exactly the same kinetic energy, but they're both not going the same speed in terms of the diffusion because they have different molar masses. The particles are different masses. If they have different weights or different masses, then they're going to travel at different speeds, even with the same energy. This process of traveling is essentially the particles are going in a direction until they bump into something else, like another gas particle. For example, if I have this perfume diffusing through the air, the perfume molecule would travel until it bumped into an air molecule, and then it would bump off, and you would see sort of a back and forth motion, and eventually the particles are going to move through the room in this fashion. Alright, when I'm looking at the same temperature, if I have two different types of particles, again, they do not diffuse at the same speed, although they both have the same kinetic energy. And in general, the higher the molar mass, or the heavier the molecule is, the slower it goes. And that kind of makes sense, all right? Heavier items maybe move a little slower than lighter items or objects would. So a smaller molar mass, something that is lighter, is going to move faster. There's an equation that relates these, and this is known as Graham's law, but I want to talk about it in terms of a process different from diffusion. I want to talk about effusion. Alright, so now we're going to look at the process of effusion. A technique that scientists use to separate mixtures of gases is a technique called effusion. Essentially, it's the same thing as diffusion, the gas moving through an open space, except for in this case, I've contained the gas to a container, and I have two sides to the container. On this side, I have originally a vacuum. I think that's how you spell it. And a pinhole. It doesn't look much like a pinhole, but I'm trying to draw it to scale here. These are the particles of gas. A pinhole between the side of the container where the gas is present and the side of the container that originally has the vacuum. Now what's going to happen is these particles that make up this gas, whatever it is, this for example could be some diatomic gas like oxygen or hydrogen. These particles are all moving around, bouncing around the container, And eventually, some of them will bop through the hole, the pinhole in the container they can fit, and start occupying this side of the container. Now, only the ones that are moving through the hole will make it to the other side. If I look at a sample of gas, all just one type of gas, again, its effusion speed depends on its molar mass, and so we can use this to effectively separate two different gases by working on this process over and over and over again. For example, let's say I have two different gases in this container now, and alright, so I've got the red gas and I've got the orange gas, and let's say the orange gas is lighter than the red gas. Just as the red gas is moving around, the orange gas is also moving around, bopping around, and again, eventually some of the particles will bop through the pinhole, and I will end up with, orange gases over here. Alright. If the orange gas particles are lighter than the red gas particles, then more of the orange gas particles will move to the right, where there was originally a vacuum, than red gas particles. I could then collect this side, I could collect this gas, which is enriched in orange particles because more of them made it over in some given time, and then I could turn around and run this experiment again. And if I start with this starting point with it already enriched in orange gas, and I put it in a container where one side has a vacuum and there's a pinhole, then I can run the process of effusion, let the gas effuse through the pinhole, and I would end up with a sample that was even more enriched in orange gas. And so this is the process that we use to enrich the gas in one particular gas versus the other. Something that we might talk about in class is this is how we enrich isotopes. If we have gases that are made up of elements that are different isotopes of the same element, the heavier isotopes will move more slowly than the lighter isotopes, and there's not a whole lot of difference in the masses of those, but there is a difference, and so we can actually enrich the gas in a particular isotope, and this is one of the techniques we use to enrich isotopes. Alright, bottom line, the formula for using this fact comes from the fact that the rate of the effusion or diffusion, which is a speed, is proportional to 1 divided by the square root of the molar mass. Here my big M stands for the molar mass. In fact, let me do this, molar mass. It's inversely related to the molar mass. Again, the heavier the particle, the slower it moves, but it's not a directly inverse relationship. It goes by the square root of the molar mass. So if I have two gases that I'm trying to effuse, I can use the formula the rate of gas 1 divided by the rate of gas 2 will equal the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. You'll notice that rate 1 is on top, molar mass of 1 is on bottom, and vice versa. So in an equation, I might be given the speed of both gases and the molar mass of 1. I would solve for the molar mass of the unknown gas. Or I might be given both gases so I could find their molar masses, and I might be looking for the speed that one of them would travel at versus the other. So again, 4 variables here. You're going to have the problem set up such that you know 3 of them and you're solving for the one unknown.